In Part 3 of our Test 1 review, we're going to start taking a look at the Chapter 2 problems. This video will cover problems 11 through 16. In problem number 11, we're given this graph and asked to determine whether or not the graph represents a function and to explain our answer in a complete sentence. Since we're given a graph, that means that we should use the vertical line test. So, the idea is that we should draw a vertical line on our picture and determine whether or not our function passes the test. In this particular case, we can see that it doesn't, because any vertical line we draw in the center of this graph is going to cut through the graph in two places. So when we write our answer, we should say that the graph does not represent a function and then for our reason, we say because it fails the vertical line test. And that's all there is to problem number 11. For problem number 12, we're given a piecewise defined function, f of x equals x subtract 4 for x less than or equal to 0, and minus x plus 3 for x greater than 0. And we're asked to sketch the graph and label the x and y intercepts. So first, we need to lay out our coordinate plane. Now that I've got my coordinate plane sketched out, I need to actually draw my function. So first I'm going to look at the top piece. X subtract 4 for x is less than or equal to 0. Since this is given in slope-intercept form, I can see that the y-intercept is going to be the ordered pair 0, negative 4. So I'm going to go ahead and plot it on the graph. So there's my point 0, negative 4. And I'll label it since it is my y-intercept. This graph has a slope of positive 1, and I'm only drawing it for values of x less than or equal to 0. So I can put another ordered pair right here at negative 1, negative 5 and connect the dots. And now I have the first part of my picture. The second part of my picture is given by the formula f of x equals negative x plus 3 for x is greater than 0. So I can see that if this part did have a y-intercept, it would occur at 0, positive 3. But since for this part of the function x is not actually allowed to equal 0, I don't actually include that point on my graph. So I can represent that with an open circle at 0, 3. I'm not actually labeling that point because it's not actually a y-intercept, and that's what the open circle is indicating. Now, this has a negative slope for x is greater than 0, so I'm going to go ahead and figure out what the x-intercept would be. So 0 equals negative x plus 3, and that says x is equal to 3. So that means I'm going to come over here and plot a point at 3, 0, and that's my x-intercept. This is filled in solid because it actually does exist on the graph. And now I can connect the dots. And I have the second part of my piecewise defined function with my x and y intercepts labeled. In problem number 13, I'm given the function y equals the square root of the quantity 12 minus x and asked to state the domain and the range of the function in interval notation. So let's start out with the domain. For the domain, I need to actually be able to evaluate the square root of 12 minus x. In order to be able to do that, I know that 12 minus x has to be greater than or equal to 0. So I need to solve this inequality for x. So that says 12 is greater than or equal to x, and I now have my domain. So the domain for this function is all x's that are smaller than or equal to 12. So that's the interval from minus infinity to positive 12. Since minus infinity is not a number, it gets a parenthesis, and since x can actually equal 12, the 12 on the upper end of my interval gets a square bracket. Now let's think about the range. The range is all the values that y can take on. Since y is equal to a square root, that means the smallest possible value for y is 0. And of course, square roots can get as large as they want, so 0 is less than or equal to y, or as an interval, 0 to infinity. Since y can actually equal 0 when x is 12, the 0 gets a square bracket, and because infinity is not a number, it gets a parenthesis. So this is the range. Problem number 14 says, suppose the graph of y equals square root of x is vertically stretched by a factor of 5, shifted right 3 units, and then shifted down 4 units. Write the equation of the new graph. So let's take this apart piece by piece. First, we're asked to vertically stretch the graph by a factor of 5. That means that all our y values will be 5 times bigger. So we multiply the entire equation by 5. So there's step 1. Step 2 says we're going to shift right 3 units. That means we're only going to be affecting the x. So this change is going to happen underneath of the radical. Since we're moving to the right, we need to subtract. So the under part of the radical now says x subtract 3. Finally, it says we're going to shift the graph downward 4 units. This affects the entire equation, so we're going to take 5 times the square root of x subtract 3 and subtract 4 from the entire equation. So our final version of our formula is y equals 5 times the square root of x subtract 3 minus 4. In problem 15, we are asked to determine algebraically whether the following function is even, odd, or neither, and we're given y equals 4x to the 5th power minus 2x cubed plus 1. So our rules for algebraically determining whether functions are even and odd is that f of minus x is equal to f of x if our function is an even function, and f of minus x equals the opposite of f of x for all the x's in the domain if our function is odd. So let's take a look at f of minus x for our function. It'll be 4 times the opposite of x raised to the 5th power minus 2 times the opposite of x cubed plus 1. Going through and cleaning this up, since we're raising minus x to the 5th power in the first term, the negative sign will stay, so we'll have the opposite of 4x to the 5th power. Something similar happens in the middle term. We have minus x cubed, so again, because of the odd power, the minus sign is going to stay, so that means we have two negatives multiplied together, which gives us a plus 2x cubed, and our constant term stays the same. So we can now see that f of minus x is not the same as f of x, because our first term and our middle term have different signs on them. We can also see that f of minus x is not equal to the opposite of f of x, because the sign on the third term, the plus 1, did not change. That means that this function is neither even nor odd. In problem 16, we're asked to find and simplify the difference quotient for f of x equals x squared minus 2x plus 4. So in order to find the difference quotient, we need to find f of x plus h and plug it along with f of x into the difference quotient formula. So for f of x plus h, we need to replace all the x's in our function with the quantity x plus h. So that'll be x plus h squared minus 2 times x plus h plus 4. And then we're going to subtract f of x, which was x squared minus 2x plus 4. Notice that I put f of x in parentheses because I'm subtracting the entire function. Then I'm going to take this difference and divide it by h. So now I need to go ahead and simplify my numerator. So I'm going to expand x plus h, the quantity squared. That's x squared plus 2xh plus h squared. I also need to distribute minus 2 across x plus h. So I now have minus 2x minus 2h plus 4. And now I need to distribute the minus sign across f of x, which will give me minus x squared plus 2x minus 4. And all of this is still over h. Now I'm going to go ahead and look for like terms to combine. What I want to notice is that any term which does not have a factor of h should have something to cancel with. So x squared and minus x squared cancel. Minus 2x and plus 2x cancel. And plus 4 and minus 4 cancel. So that means that I'm left with 2xh plus h squared minus 2h all over h. Now I can factor h out of the numerator. So that'll be h times the quantity 2x plus h subtract 2. This means that the factor of h in the numerator and the factor of h in the denominator divide to 1, which leaves me with 2x plus h subtract 2 as my difference quotient.